first one. And it's our pleasure to welcome Wen-Chau Lee. Wen-Chau got his bachelor's from National Taiwan University in atmospheric sciences, stayed in the field, getting master's and PhDs at UCLA. And pretty much since he's gotten his PhD, he's been at NCAR. First as a GRA, then a postdoc, and now he's a senior scientist, and for the last 4 years has been managing the remote sensing facility. Wen-Chau's also been doing a lot of educational activities along the way, mentoring lots of students and giving lots of lectures. So we get the honor of having one on his DVAD. Thank you, Wen-Chau.
Well, thank you for coming. I changed my title slightly. I added forgotten thing there. Okay. I'll explain why I add that word. Depends on who you talk to. It can be new, it can be forgotten. Okay. Now, Rick comes, it's forgotten. Okay. Okay, so I'll first tell you why we want to do this. And since it's called Distance Velocity Azimuth Display, I'll review some basics about the VAD technique and illustrate why this new or forgotten framework it can review more information and easier to interpret the results, and I give a summary of future work. And this talk is based on the paper published in Monthly Review last year. So first, I don't need to tell everybody about Doppler radars. And all of our Doppler radar analysis are pretty much based on this equation. Doppler velocity is a projection of u, v, w. This w can include the terminal fall speed, and theta is the azimuth angle, phi is the elevation angle. So Doppler velocity is pretty much a spherical coordinate concept, sort of a vector. Depends on which direction you look. It may give you different answers for the actual wind field. So if you write it into x and y and z, Cartesian coordinate, you can write it in this form. So there's nothing new about this equation, and you can see that on the right-hand side of the equation, there is a 1 over r in every term. So basically, the distance velocity azimuth display, what I'm going to talk about today, is basically multiply r to the other side of the equation. So it becomes r times vd. Okay. So this work, this is a ranking vortex, wind field of a ranking vortex. So this is a Doppler radar observation of this ranking vortex with the radar located at 0 and 0. So this is the receding velocity, this is the approaching velocity, and the standard dipole has been known for many years. What you can see is because of the FAM PPI scanning of the radar, so the dipole is somewhat distorted. Okay. About 20 years ago, Benjo and I, which I want to recognize my co-author, we found that if you display the Doppler velocity in this manner, which is r times vd scaled by rt. Rt is the radar to the tropical cyclone center, the distance. You get a symmetric dipole in this form for a ranking vortex. In the literature, we have many papers discuss how to compensate for this Doppler dipole distortion to identify the center of a vortex by Doppler radar observations. But if you're displaying this form a ranking vortex, you can just draw a line between the maximum and minimum Doppler velocity, and it runs through the center of the vortex. In this framework, the distortion of the Doppler radar velocity disappear, okay, in a different framework. About 10 years ago, when we worked on this 2008 paper, we looked at the equation more closely and actually found that this R times VD, if it is a uniform wind field. So in this case, it's a easterly wind from east to west. Radar is here. So the Doppler velocity is more of a diverging pattern. So you have maximum approaching velocity at 90 degree, maximum receding at 180 degree, zero Doppler velocity north and south. However, if you display the velocity into this R times VD framework, it becomes a set of straight lines, parallel lines. Okay. So this result made us think, okay, in addition to applying this framework into a vortex situation, can we apply it to a more general non-vortex situation? So that lead to this presentation. However, I have to acknowledge that we are not the first one who recognized this nice relationship. The first paper, Peace et al., 1969. Okay, first multiply R to the other side. He used this to deduce a pseudo Doppler analysis for a convective storm using single Doppler radar. Another pioneer, Gao Chen, 1982, in his paper, he mentioned that R times VD can be used to do the advection of the storm before you do the Doppler analysis. Okay, and by talking to Rit, Gao Chen talked to him about a lot more, but I didn't know what it talked about. Only this paper was published that Rit told me that Gao Chen told him a lot about what I did. Okay, but it's not, I don't think it's officially published in any journal. So I have to recognize these. That's why I changed my title a little bit from new, quote, forgotten. Okay. So I read those papers when I was a graduate student, but it didn't really ring the bell. Why R times VD is such a nice relationship. Next, with a room of Doppler radar experts, I'm going to give you some tests. This has been illustrated. This is a diverging pattern of a Doppler velocity. Radar is located at the center. So this is simple. It's a constant wind. Next one. Okay. The redder color means higher Doppler velocity. So this is not difficult at all. It's a diverging pattern where the divergence center is at the radar. So the velocity is equally increasing in all directions. This is a little bit more difficult. Okay, this is still a diverging pattern, but with different magnitude on the du dx and dv dy. Okay. So it looks like a ellipse. Now this is a little bit more complicated. Okay, so what is this doing? This distortion. This is actually a divergence, which is this pattern, plus a background mean wind. Okay. Another one. Both plots look like hyperbola. But this one represents a convergence-divergence pattern, which flow moves in from this direction and flowing out this direction. This one actually represents a stretching deformation. Okay. So my point is, by knowing the linear wind field and construct the Doppler velocity, you know the pattern. But the question is, how do we go the other way around by looking at the Doppler velocity pattern and try to understand what's the wind field surrounding the radar? So one of the main challenges has been to extract key kinematic properties of a wind field from a given single Doppler radar observations. There are many single Doppler wind retrieval algorithms has been developed based on simplified wind field. For example, a linear wind field or a circular wind field and all that. One of the pioneer is the VAD analysis. The first paper appeared in the conference papers by Lermin and Atlas, but the journal paper version is by Browning and Waxler in 1968. This technique has been widely used in research and operational radar environments and becomes a standard NextRad algorithm. So if you go to any NextRad site, radar site, you can find a time series of the VAD vertical wind profile on that. So the next couple minutes, I'm going to go through, review some simple basic kinematic properties and discuss what VAD is all about. So any wind field U and V in 2 dimensions can be expanded into Taylor series. So this is the 0th order term, mean quantity. This is the first order derivative and higher order derivatives. So if we only consider the linear terms and do some manipulation, this shouldn't be a stranger to most of you, which is a standard synoptic meteorology textbook has this, then you can derive this equation, which consists of 5 key properties of a linear wind field, including the translation term, divergence term, vorticity term, stretching deformation, and shearing deformation. In the vector form, you can write it in this way. So quickly go through what each term means. A translation means a parcel is moving by the environment wind. Okay, a wind field, U and V. Parcel shape doesn't change, only location change. A convergence divergence means the area of the parcel will change. Vorticity means the direction of the parcel will change. Stretching deformation, the area will not change, but the shape change. And shearing deformation is the same. So let's get to the VAD analysis. Okay. This is one of the most popular technique, that's single Doppler retrieval technique. It's been used in the community. And this technique is centered at the radar. Here. So with a PPI scan, elevation angle alpha, if we look at a constant radius, which we call a VAD ring, any velocity at a point of alpha and theta can be decomposed into 3-dimensional velocity, u, v, w, and terminal fall speed. And the Doppler velocity VR can be expressed in terms of this relationship, which are already seen in the Armijo 1969 paper. So for a wind field which is quasi-linearly vary across this domain, which can be expressed like this, if we plug this equation into here and use the trigonometry functions to represent x into r cosine beta, y equal r sine beta, and use the trigonometry identity, here is the physical equation we obtain for the radial velocity Vd. And you can see this Vd is a function of beta, which is the azimuth angle, and also is a function of alpha. So at a constant elevation angle alpha, Vd is a function of beta, which is the azimuth angle. So if we expand VD into Fourier series, and this is the equation that we obtained earlier. So if we match the coefficient between these two equations, this is a physical equation, this is a mathematic model of the wind field. By comparing the coefficient, we can obtain the VAD coefficients. A0, A1, B1, A2, and B2 are composed of different kinematic properties of the linear wind field. A0 is basically the convergence-divergence term plus a vertical component projected into the radial velocity, radial direction. The A1, B1 represent what we call the mean wind, U0 and V0. A2 and B2 represent the deformation field. Okay, so this is the essence of how we can use VAD technique to recover some basic flow patterns in the atmosphere. Schematically, this is a diagram copied from the Browning and Wexler 1968 paper. So for the zeros harmonic, which means a line deviate up and down from the y-axis, that represents the divergence and the fall speed component of a particle. For wave number 1, if you do the Fourier decomposition of the radial velocity along a constant VAD ring, wave number 1 has a signature like this. Okay. So this curve represents the translation component of the wind field, including the direction and the speed. And wave number 2 component consists of the deformation information. Okay. So this diagram shows if we plot all the Doppler velocities along a constant VAD ring and do a Fourier decomposition, you can resolve the wave number 0 component, wave number 1 component, and wave number 2 component. You can, in theory, you can decompose into even higher wave numbers. But later on, I'll show you a work by Kaya and Zawadzki that expanding to even higher wave number doesn't have much more physical meaning in the coefficient. So this is what I mentioned earlier. In any next-red site, you can find a VAD vertical wind profile with time. Okay. So basically, VAD wind profile has been used to examine the evolution of the wind field on top of a radar site. The VAD analysis has many constraints. The first one is the accuracy of the flow model. Okay. The flow model is a mathematical model that I mentioned earlier. Okay. If your flow model is incorrect or cannot represent your flow field, then it doesn't matter how you do the Fourier decomposition, you will not get the right answer. The de-aliasing is a big issue, velocity folding. Uneven data distribution. The good thing about sine and cosine, they are orthogonal functions. However, they are orthogonal only if the distribution is evenly of the data point. When you have data gaps, technically it's not orthogonal function anymore. Also, we have a choice of weighting functions. You can assign different weights on different velocities. As I mentioned earlier, data gaps for VAD analysis, you probably don't want to have a data gap bigger than 30 to 45 degrees. Now, let's move to distance velocity azimuth display. Maybe it's a new paradigm. So, this is the original equation for Doppler velocity. 1 over r multiplied this. This is spherical coordinate concept. If you multiply r over here, r times vd is a Cartesian coordinate concept. So you can process r times vd in x, y, and z coordinates more than in spherical coordinates. If we take the gradient of r times vd, do the manipulation, you get the velocity vector plus a bunch of vectors related to the derivative of the velocity field. So to some extent, R times Vd behaves like a velocity potential. Because if you take a gradient, there's a velocity term plus some other things. One thing I want to point out is that at the origin, which is a radar, where x, y, z equals 0, gradient of RVD is the velocity vector. No assumption is involved. Okay. So practically, if you have a field R times Vd, and you evaluate this gradient at x, y, z equals 0, you get a wind field. This is how you can obtain the vertical wind profile without any assumption. So, if we expand the polynomial into higher order terms and substitute this equation into this form, I only illustrate the result in 2 dimensions for a linear wind field. This is what we have. For a linear wind field, R times Vd is in this form, which has x squared, x times y, y squared, x and y. This is a quadratic equation. The coefficient of this quadratic equation is ux. This is the deformation field, vy, u naught, and v naught. Okay. By comparing with the Fourier, the VAD analysis, you can see we actually recover almost everything identical with the VAD formulation, just in a different form. This shouldn't be a surprise. R times Vd is essentially a coordinate transformation. Okay, coordinate transformation should not give you more information than its original form, but the information is displayed in a somewhat different shape. Okay. So, however, in this form, you can see the shape of R times Vd. This is a determinant of this quadratic equation. If d is less than 0, it's either a circle or ellipse. D equals 0 is a parabola. D greater than 0 is a hyperbola. So in R times Vd framework, the linear wind field becomes very easy to recognize. Okay. The Doppler velocity, I cannot show. It has this nice form. Okay, let's look at the quadratic equation a little bit more. So R times Vd is in this form, and we can write it as this. So we merge the u naught and v naught, x and y terms into the second order term. So essentially, these 2 terms is a shift of location of this quadratic or the conical section. Okay, you shift your circle, ellipse, parabola, or hyperbola away from your grid origin to somewhere else. These are the x and y terms actually represent. So if you write the equation in this form, you can see a shift of the center of your feature in here. So manipulating these coefficient f can be represented in this form, and the x naught, y naught can be represented in this form. So one thing I want to point out is in the VAD analysis, because it's radar-centric, okay, there's no information of where that system is located. For example, a microburst. If a microburst just landed right on top of the radar versus a microburst landed like ESPO or landed over FL2, okay, the signature in the VAD will be very similar. Okay. But in a linear sense, divergence should be the same no matter where that center is located. However, the vertical wind field at the radar side will change, depends on where that system is. Okay. So the location of the system is interpreted as a environmental mean wind. So you can imagine that if there's a microburst that's moving with time, the wind field at the radar derived by the VAD will change, even though the divergence remains constant, or the microburst intensity remains constant. Okay. So is that the change of environment wind, or it's because the moving of a system? Okay. So this is the ambiguity that's involving in the VAD analysis. Also here, this framework cannot help you to separate these two factors, but the equation can clearly tell you they are tangled together. Okay. So the point is, how do we interpret the vertical wind profile obtained by the VAD analysis? Okay. This is a very interesting question. Let's do a little bit more. For the quadratic equation, we can rotate the system by this factor and remove the x and xy term. So the equation will become here. We can also show that a plus c in this form should be equal to the ux plus vy in our original equation. Okay, it can be shown. What does this mean? This means the divergence is coordinate independent, it's invariant. Doesn't matter which coordinate you're looking at. Okay, divergence is always the same. However, the rotation can make the deformation term disappear. So the deformation is coordinate dependent. Okay, I'm not telling you anything new. This is a well-known fact in the synoptic meteorology textbook. I'm just using Doppler radar data to illustrate that the same information can be derived in this form if we use the R times VD framework. So I'll give you several examples of the R times VD versus Doppler velocity. So we have seen this. Constant wind field. This is the Doppler velocity. This is R times VD. This factor means the gradient of the R times VD represent the wind vector. So we can show it mathematically. R times VD, ux times vy. If u equals c1, v equals c2, and you take the gradient, you get c1i plus c2j, which is the velocity vector. Okay, so this is a very simple relationship. Now, you have seen all three of this. I illustrated earlier. I used the magnitude of divergence in the mesoscale, about 10 to the minus 4 per second, to illustrate. So this is a divergence field with the magnitude greater in the x direction than the y direction. You can see R times VD, as I showed you earlier, is an ellipse. Okay, I cannot show this is the ellipse, so I'll refer this to an elliptical type curve. Okay, this is also a divergence, but the flow is coming this direction and going out this direction. So this is more of a hyperbola type like curve, and this is exact. You can show in the equation that this is a hyperbola form. Deformation field. So you have flow coming from northwest and southeast and flowing out northeast and southwest. So Doppler velocity, R times VD. Okay. So the point here is, if you display your Doppler velocity in the R times VD framework, you can visually, graphically figure out what's the key properties, kinematic properties in the wind field. Okay, it's very easy to recognize it if the wind field is linear. A little bit more complicated. Okay, if we merge two types of wind field, atmosphere rarely just throw you a microburst without anything else. So this is an example of divergence plus some deformation. In the Doppler velocity field, you can see it's hard to recognize any dominant shape. It's an elliptical type. But in the r times vd coordinates, the shape remain. It's an ellipse with a rotation. Okay. Same here for a different divergence field plus the same deformation field. It's a hyperbola with a rotation. Okay. So these basic shape can be sort of a manual, and the operator or scientist can look at these patterns and understand what's the important kinematic properties of the wind around the radar. So when we have divergence plus mean wind, as I illustrated earlier, this is a strange shape. In the r times vd framework, it's a displacement of the ellipse, as I illustrated earlier in the equation. Okay, so the shape is conserved with the mean wind, or if the center of your circulation is not located at the radar site. Oops. Okay, similar expression plus the mean wind. In the Doppler velocity framework, the shape becomes much more difficult to recognize, but in the r times vd framework, it's basically a shift of your basic shape of the hyperbola. This is probably the most complicated case I'll show you. It's a divergence plus deformation plus mean wind. Again, take-home message is that in the Doppler velocity framework, the shape is distorted, but in the r times vd framework, the shape is conserved. Okay, it involves a rotation plus a translation of the pattern. So what if we add a second-order nonlinear wind in there? What will the shape change? So, I mean, this is a cubical equation. Okay, and the shape is hard to recognize. There's so many nonlinear terms. So I'm just going to illustrate having a term of uxx as an example. So I input a value of uxx about 10 to the minus 7 versus 10 to the minus 6. So the nonlinear effect is bigger on the bottom and smaller on top. You can see in the r times vd framework, when the nonlinear term is relatively small, the shape is still there. You can recognize it as a quadratic equation. But when the nonlinear term is getting bigger, you don't see that nice shape anymore. So another way about using r times vd is it's relatively easy to tell whether the wind field is linear or nonlinear, or which components are important. When a nonlinear wind field dominates, you shouldn't see any nice shape like a quadratic equation. So how do we do the computation? Okay. With this nice quadratic equation, so there are many ways different ways to extract information out of it. Okay, I'll just illustrate two of them. One is the two-dimensional polynomial curve fit. So you can fit the Doppler velocity on the constant altitude, or the PPI, with that polynomial, two-dimensional polynomial equation. Where do you stop? You can use the f-test to see the majority of amplitude has been resolved in your coefficient, the low-order coefficients. The other one is somewhat interesting, because this is a polynomial equation. So you can actually do a differentiation. You can differentiate the equation. Okay. In the VAD form, because it's sine cosine. So no matter how you differentiate it, the theta term is always there. Okay, no terms will disappear. But in the polynomial terms, every time you do a differentiation, certain terms will drop out. Okay, I just use the linear term as an example. So these two illustrate I differentiate x with respect to x and y on that quadratic equation. So you can see some terms drops out. And if you evaluate these values at x and y equals 0, the mean wind, or the u naught v naught, is your answer. Okay. And if you take another derivative, these term drops out, and the ux, vy, and the deformation term appear in the analysis. I just give you an example. So this is the flow field I inputted. This is the Doppler velocity, it's r times vd. And if I take a derivative, you can see, because of the linear term, the first derivative should be a constant. Okay, so it appears as a set of parallel lines. And I take a second derivative, it's a constant. Okay, so this is another way of extracting the coefficient by differentiation rather than do a curve fitting through the entire process. So I compare the two different ways of computing the coefficients. So this is an analytic wind field. The true wind field has these parameters. So if I use the two-dimensional curve fitting, this is what we resolve, and this is using the derivative method. Okay, so you can see these two methods pretty much give you the same answer with some very, very minimal uncertainties. Another point I want to make is what we call pseudo winds. If you look at the gradient of r times vd, as I illustrated earlier, it's a velocity factor plus a bunch of gradient terms. Okay. So if we look at it in two dimensions, which I call up, which is pseudo u, vp pseudo p, and you can write the equation and match the left and right-hand side in these terms. So basically, with a field of r times vd, if you take the gradient of that quantity, you basically get a horizontal velocity plus some bias. Okay. As I mentioned earlier, if you evaluate this equation at x and y equals 0, you extract the u and v unambiguously without any assumption. But you can see when x and y are small, which is closer to the radar, okay, you can actually deduce the wind field very close to the truth without much of assumption, okay, unless you are in a big deformation field right on top of the front or a microburst hitting you nearby. So this is another practical application that may be very easy to implement for radar meteorologists to understand what's going on surrounding the radar. I'll just give you an example. So this is a score line. This is reflectivity on top panel, Doppler velocity, and r times vd on the bottom panel. So this is the score line. The radar is here. We can see in front of the score line, Doppler velocity is approaching the radar and going away. So this is a southwesterly flow in front of the score line, and behind the score line we have some rear inflow pushing this part of the line forward. Okay. So if we look at the Doppler velocity, of course, I mean, you guys are all experts. It's not too difficult to figure out which direction the wind is blowing. But for an amateur, r times vd framework shows a lot of straight lines. According to the equation I showed you earlier, if you see lots of straight lines, that represent the wind is near uniform wind field. Okay. So in this sense, it's relatively easy to interpret what's going on with the wind field surrounding you. it's also interesting to note that when R times VD is not linear, this kink of the field corresponds to the location of a score line. So as I mentioned earlier, when you see this type of features, it's not either linear or quadratic form, parabolic, circular, or ellipse, then there's a lot of nonlinearity involved here. One caveat I want to mention here, the distance VAD still cannot resolve the vorticity. Okay, you have to use a different technique in order to resolve the vorticity. I just want to point out that this score line has a rotating head. There's a mesocyclone here. You can see there's a mesocyclone here. Okay, larger approaching flow, weaker approaching flow. The score line is moving this direction, so there's a mesocyclone here. But when you look at R times VD, it doesn't really show that signature. Okay, so if you use the distance VAD, you will not resolve the rotation component. You will be aliasing to other factors. Well, in the last few minutes, I want to mention the VAD analysis of nonlinear wind field. Okay, so this is the equation you have seen earlier. This is the physical flow model. This is the mathematic model we apply. In a nonlinear wind field, when we expand U and V into all these terms, this is the equation we end up with. And you can look at Kaya and Zawadzki 1992 for more detail. The point is, we can still do a Fourier decomposition to resolve the A0, A1, A2, B1, and B2. However, in a nonlinear sense, there are lots of terms appending to these basic linear quantities, as I showed you earlier. Kaya and Zawadzki show that if you do the math, these are the actual physical quantities represented by these nonlinear wind field. Okay. In the linear sense, the coefficient comparison, there's a 1-to-1 correlation. A0 with divergence, A1, B1 with U0, V0, A2 and B2 is the deformation field. However, you can see that these equations does not represent the actual physical quantity. So this is the issue with VAD when you deal with a nonlinear wind field. Those VAD coefficient doesn't really represent the physical quantity that's actually presented. So Kaya and Zawadzki find a clever way to solve this problem. So they perform VAD at each radius. And you can see these coefficients are a function of R. So he actually performed lots of VAD analysis. Then look at the distributions of A0, A1, A2, B1, B2. Do a second curve fit with respect to R. Then evaluate that function at R equals 0 in order to obtain the U0 and V0 on top of the radar site. In the DVAD framework, because it's a polynomial equation, so once you fit or use the derivative method to extract the coefficient, you can see that U0 and V0 just fall out of the equation. Okay, you don't need to do a secondary curve fit in order to extract those information. And as I mentioned earlier, we can use the F-test to determine the highest order terms required to best fit the Doppler velocity field with the polynomial equation. So let me recap what has been said so far. In the single Doppler wind retrieval technique, there are basically two types of approach. One is do a sine cosine Fourier coefficient expansion or the polynomial expansion, either center at the radar or center at somewhere else away from the radar. Then you apply a simple wind model to constrain the problem and try to fit the physical model with your mathematical model, which is the polynomial expansion or the Fourier series expansion. If your assumption is close to what's actually happening in nature, you will get very good results. Okay, so this is the key of single Doppler wind retrieval. Okay. Your physical model has to be correct, closely to your mathematical model. And let me summarize this talk. The characteristic of a forgotten R times VD and its application to a single Doppler analysis are presented. Okay, again, I need to give credit to Peace et al. 1969 and Gao Chen. Okay. They actually pointed this out earlier, but they didn't get into the detail, as far as I know, about this parameter, application of this parameter to the Doppler velocity. The wind patterns are easier to identify and interpret graphically. Okay. For a linear wind field, the R times VD is a form of quadratic equation. So the Doppler velocity constant, the Doppler velocity contour will be in the form of ellipse, parabola, or hyperbola. And these quantity does not affect by the mean wind, i.e. the shape is conserved, whether you have mean wind or not. And R times VD can be analyzed in Cartesian coordinate, and physical quantities are easy to deduce compared with the VAD algorithm, especially in a nonlinear wind field situation. Okay, that was the last part of my presentation. Finally, the full capability of R times VD still need to be further explored. Okay, how do we interpret the vertical wind profile? Now we know that in the equation, the location of the center of your circulation can be misinterpreted as the mean wind. Okay, so if we look at a time series of this analysis, can we extract more information about what's happening surrounding you? Either the system is moving away or the system stays here intensifying, decaying, or both. Okay, I think this framework pretty much opened a door for us to have that type of discussion. One big thing that I did not touch upon is unfolding. How well the DVAD deal with the folded velocity? Okay, that's something that we need to explore. How about data assimilation? Now R times VD is in Cartesian coordinates. I don't know whether the experts here can find some use of this two quantity and may simplify the equation. I don't know. I'm looking for your input. Thank you.
Questions for Wen-Chau? It's just simply the Doppler velocity times the radius, is that?
Yes, times the distance to each gate. So it's an unevenly scaled quantity.
Right. Okay. And that's the simple transformation. So shouldn't we just at least display that?
I asked you whether we can do it in solo. You never answered. I think it was a try because I've looked at some analytic functions. It would be very interesting to see how we actually see in the real wind field when everything is mixed together. Yes, yes. Equations are all here.
Yeah, Wen-Chau, actually, I have been thinking through all your talks that it may improve the data assimilation because it's like a scaling factor. The scaling factor will change the condition of the cost function. So to me, it looks like it makes the system less aware where the radar is. You know, it's actually where the radar is. It's extreme point. It's quite dangerous. If you don't have the background wind, for example, then there it's very difficult to do the analysis in the data assimilation. But of course, we always start from some background. Like Worf tell you approximately, you know, the mean wind, so that helps. But I think by adding that, you know, instead of assimilate VD, we assimilate RAD. It's like scaling factor there. So I think it may help, actually. We should try.
Okay,
Yeah.
good. But I think the concept of pseudo wind can serve as a background.
Yeah.
Okay, because it's unless you have a big synoptic system close to the radar,
Yeah.
otherwise it should provide you pretty good background wind field.
Yeah, that's right.
This is a comment more than a question. When you multiply the radial velocity by r, you're effectively causing the radial velocity to behave without direction in the Cartesian coordinate system. And that's really the key in the physics of that.
Right.
Because in your very first equation of u, x over r, and the like, when you multiply both sides by r, you've removed the implicit directionality of the radial velocity whenever you display it. And that's really the key. So if you multiply by the r, then you end up seeing something that looks like a regular component of the wind.
Yes.
Or a scalar.
It's a scalar. That's the key.
No directionality.
Right. So let's go back to give credit to Gao Chen. His 1982 paper actually mentioned that if you want to advect a Doppler velocity, you're better doing the R times VD framework rather than R. And of course, 20 years later, I finally fully appreciate why he said that.
Well, that's actually why we do the advection within the synthesis in Cedric, by doing that multiplication by R, so that we can advect during the synthesis and treat it as a scalar.
Okay. I think that's a major difference. And another point I want to make is, I haven't figured this one out, is that we have a national composite of reflectivity, because reflectivity is a scalar, but we don't have a national composite of Doppler velocity. And in this framework, it may open the door. I haven't figured out how to match the quantity between different radars, but this is, at least this is possible now. Yeah.
Anyone else? Then let's thank Wen-Chau again.
Thank you.